A pair of dice that always add up to 7 would make you the richest person in Las Vegas. Throw them together. Throw them across a room. Send one across the Pacific with a friend, and the two numbers still complete each other every single time. A 2 here, a 5 there, a 1 here, a 6 there, forever. And yet each die, thrown on its own 10,000 times, is perfectly fair. Nothing is loaded. Nothing is signaling. Objects that behave exactly like this have been manufactured in physics laboratories since 1972, and the experiments showing that they cannot be carrying a secret agreement have confidence levels of about 1 in a number with 31 zeros after it. But here is what almost every account of this leaves out. The argument that rules out the agreement rests on 3 assumptions, not 2, and the third one has never been tested, can never be tested, and quietly concerns you. There is a third explanation for the dice, and by the end of tonight, you will know exactly what it is and exactly what it would cost. Before we begin, if having something this ordinary taken apart this slowly is how you like to fall asleep, a quick like or subscribe really helps the channel grow. It costs you nothing, and it means the world to me. Now, let's begin. Imagine that you find a pair of dice that always add up to 7. Not usually, not on average, always. You can throw them across a table, drop them down a staircase, seal them in separate boxes, and have them shaken by strangers who have never met. And when you finally look, the two numbers showing will add up to 7. A 1 and a 6, a 3 and a 4, a 5 and a 2, every single time, without exception, forever. Take a moment with that object, because it is stranger than it first appears, and the strangeness is not where most people expect it to be. The first thing you would check is whether the dice are simply loaded. Weighted dice are an old trick, and they are easy to catch. A loaded die does not produce a uniform spread of numbers. It favors one face, or 2, and after a few hundred throws, the bias shows up in the tally as clearly as a fingerprint. So you throw one of your dice, on its own, 10,000 times, and you count. 1 comes up roughly 1 time in 6, 2 comes up roughly 1 time in 6, 3, 4, 5 and 6, the same. The individual die is as fair as any die that has ever been manufactured. There is nothing wrong with it at all. You could take it to any casino in the world, and no inspector would find a thing. Then you throw the other one, on its own, 10,000 times. Perfectly fair as well. So each die, considered by itself, is a machine for producing pure randomness. Neither of them has a preference, neither of them has a pattern. And yet the moment you throw them together, the two random results lock into a relationship that cannot be broken. 7, every time. Now separate them. This is where the object stops being merely odd and starts being impossible. You keep one die in Las Vegas. Your friend Alice takes the other one to Macau, which is about 7,000 miles away, across most of the Pacific Ocean. You agree on a moment. When that moment arrives, you throw your die on a felt table in a quiet room, and you watch it settle, and it shows a 2. And in that instant, without checking, without a phone call, without any way of finding out, you know something about a small cube of plastic on the other side of the world. You know it is showing a 5, not probably, not most likely. It is showing a 5, and when Alice photographs it and sends you the picture some hours later, it is showing a 5. Nothing in that sequence, taken one piece at a time, is impossible. What is impossible is the combination. Each die is genuinely random on its own, and yet the two of them are perfectly coordinated. Those two facts do not sit comfortably together, and almost everyone who hears the story reaches immediately for the same explanation. The obvious answer is that the dice agreed in advance. Before they were separated, back when they were sitting next to each other on the same table, they must have worked something out. Your die decided, somehow, that on the next throw it would show a 2, and the other die decided that it would show a 5, and each of them carried that decision with it. quietly, all the way to the destination. When you threw yours, you were not generating a number. You were reading one that had been written months ago and carried in a pocket. There is nothing spooky about that at all. It is exactly what happens if you tear a photograph in half, put the two halves in two envelopes, shuffle them, and mail one to Macau. When you open your envelope and see the left half, you learn instantly what is inside an envelope 7,000 miles away, and no physicist anywhere finds that troubling. The information was always in the envelopes. Opening one just told you which was which. Hold on to that explanation. It is the natural one. It is the one almost every thoughtful person produces, within about 10 seconds. And it was also the explanation preferred by the most famous physicist who ever lived. It is going to be the center of this entire story, and it is going to turn out to be wrong, in a way that is far more interesting than it being right. Because there is a second explanation, and the second explanation is the one that gets all the attention. Perhaps the dice did not agree in advance. Perhaps neither of them had a number at all, until one of them landed, and at the instant your die settled on a 2, something reached across the Pacific and made the other one a 5. Something faster than light. Something that does not care about distance. Something, in other words, that would tear a hole straight through the physics we have been using with total success for 120 years. Those are the two options everybody talks about. Either the answer was written down in advance, or a message traveled impossibly fast. And the reason this video exists is that the first option has been ruled out by experiment, the second option has been ruled out by theory, and almost nobody mentions that there is a third. Now, dice like this do not exist. You cannot buy them, and you would not want to explain to a casino how you came by them. But the reason the story is worth telling is that the quantum version of those dice is completely real. It is not a thought experiment, not an analogy, and not a speculation about what might one day be possible. Pairs of particles behaving exactly this way have been manufactured in laboratories since the early 1970s. They are made routinely, in the thousands, in university basements. There are machines that produce them on demand, the way a tap produces water. Right now, as you are lying there listening to this, there are almost certainly several such pairs in existence within a few hundred miles of you, sitting inside some cryostat in some physics department, being measured. The particles are usually photons, which are individual pieces of light, and the property that plays the role of the number on the die is usually something called polarization. But the structure of the situation is identical. Each photon, measured alone, gives a result that is genuinely random. The two photons measured together give results that are perfectly related. The relationship survives separation. It has been tested at 10 meters, at 1.3 kilometers, at 144 kilometers between two islands, and via satellite over more than 1,000 kilometers. It has never once failed. And the question of what that relationship actually is has been the most carefully investigated question in the history of physics, not the most funded and not the most famous, but the most carefully investigated, in the specific sense that people have spent 60 years methodically eliminating every possible ordinary explanation, one at a time, closing each escape route with a purpose-built experiment. The confidence levels involved are extraordinary. In 2015, one of these experiments produced a result whose probability of occurring by chance was about 1 in a number with 31 zeros after it. There is no other claim about the fundamental nature of reality that has ever been supported by evidence that strong. So here is where we begin. Two objects, each one behaving randomly, both of them perfectly coordinated across any distance you care to arrange. And the two available explanations are that they carried an agreement, which experiment says they did not, or that something traveled faster than light, which the rest of physics says is impossible, and which, as we will see, would not actually help even if it happened. If no agreement was carried, and no message was sent, then what is left? There is an answer to that question. It has a name. It was described, in careful detail, by the very physicist whose work ruled out the first explanation, and having described it, he spent the rest of his life hoping it was not true. Almost no working physicist today accepts it. A small number of extremely serious ones do, including a Nobel laureate. And the reason it is so widely rejected has very little to do with the physics, and a great deal to do with what it would mean about you, lying there, listening to this, and about whether the next thing you decide to do is something you are going to decide. We are not going to answer it yet. By the end of tonight, you will know exactly what that third explanation is, and exactly what it would cost. But we have to build up to it slowly, because it only makes sense once you understand precisely what has been proven and, far more importantly, precisely what has not. And to get there, we have to go back before the pair, to the single die, because before you can understand what two entangled particles are doing, you have to understand what one particle is doing when nobody is looking at it. And the honest answer to that, according to our best theory of the physical world, is that it is not doing anything at all. Picture a single die spinning in the air, halfway through a throw. There is a tempting way to describe what is happening, and it is worth saying out loud because it is nearly right, and the small place where it is wrong is the whole of quantum mechanics. The tempting description is this: while the die is in the air, it is a 1 and a 2 and a 3 and a 4 and a 5 and a 6, all at the same time, and when it lands, it becomes just one of them. That picture is useful, and I am going to keep using it, but I want to be honest about what it is smuggling in. A real die tumbling through the air does have a definite orientation at every instant. It is a solid object obeying Newton's laws, and if you filmed it with a fast enough camera, you could freeze any moment and read off exactly which face was pointing up. The reason you cannot predict the outcome is not that the die is undecided. It is that you do not know the exact force of the throw, the exact spin, the exact stiffness of the felt. The randomness of an ordinary die lives entirely in your ignorance. Remove the ignorance, and the randomness disappears. Now here is the difference, and it is the single most important idea in this entire subject. A quantum particle is not like that. When we say a photon has no definite polarization before it is measured, we are not saying that it has one, and we have not found out yet. We are saying that there is no fact about it to find out. The property does not exist in a hidden form, waiting to be discovered. It is not written down anywhere, not in the particle, not in the laboratory, not in the universe. There is nothing to be ignorant about. That sounds like a philosopher's distinction, a quibble about words. It is not. It is a physical difference. It produces different experimental results, and we have been watching those results for 100 years. The cleanest demonstration is the one you have probably heard of. Take a barrier with two narrow parallel slits in it, and a screen behind. Send light through, and you get a pattern of bright and dark bands on the screen, because the light going through one slit interferes with the light going through the other. Where two crests arrive together, you get brightness. Where a crest meets a trough, you get darkness. That has been understood since 1801, and there is nothing mysterious about it, as long as light is a wave. The mystery begins when you turn the source down. Turn it down far enough, and you are sending one particle of light at a time, with long gaps between them. Each one arrives at the screen as a single dot, in a single place, like a small piece of shot. And if you are patient, and you let the dots accumulate for hours, the bands come back. The interference pattern rebuilds itself out of individual particles that arrived one at a time, separated by seconds, each one apparently alone in the apparatus. There is no way to tell that story with a particle that went through one slit. A particle that went through the left slit has no way of knowing whether the right slit is open, and the pattern depends entirely on whether the right slit is open. If you close it, the bands vanish. So the particle, on its way through, was not at the left slit or at the right slit. It was not secretly at one of them and hiding it from you. And here is the part that turns a curiosity into something colder. If you install a detector that tells you which slit each particle went through, the bands disappear. Not because your detector is clumsy or heavy-handed. You can make the detection as gentle as you like, and it makes no difference. The moment the information about which path was taken exists anywhere in the world, in any form, the interference is gone, and you get two simple bright stripes, exactly as you would from ordinary bullets. Erase that information before you look, and, remarkably, the bands come back. So the existence of a fact about the particle's path is itself a physical circumstance with physical consequences. When the fact does not exist, you get one behavior. When it exists, you get another. The particle behaves differently depending on whether there is something to know. The property that matters for our dice is polarization, and it is worth spending a moment on it, because every experiment in this story is built from it, and you can partly do the demonstration at home. Light can be thought of as vibrating in a particular direction as it travels, and a polarizing filter, of the kind in a pair of sunglasses, lets through the vibration aligned one way and blocks the vibration aligned across it. Take two such filters and hold them up together in front of a lamp. Rotate one of them until they are crossed at 90 degrees. Almost no light gets through. That is the expected behavior of a pair of gates that have been closed against each other. Now take a third filter, oriented at 45 degrees, and slide it in between the two crossed ones. If you have never done this, the result is genuinely surprising. Light comes through. You have added an extra obstacle, a third barrier that can only remove light, and more light emerges than before. There is no way to explain that, with filters that simply sort photons by a property they already have. If each photon arrived carrying a fixed polarization direction like a label, then a photon that made it past the first filter would be labeled vertical, and a vertical photon would be blocked absolutely by the horizontal one at the end, and inserting anything in the middle could only make matters worse. What actually happens is that the middle filter does not sort the photon, it remakes it. A photon that passes the 45-degree filter is no longer a vertical photon with a memory of having been vertical. It is a 45-degree photon with no fact about it corresponding to the earlier question, and it now has an even chance of getting through the final filter. Measurement, in quantum mechanics, is not observation in the ordinary sense. It is not looking at something that was already there. It is an interaction that brings a definite value into existence, and afterwards the particle carries the new value and not the old one. I want to be careful about one word, because it is the source of an enormous amount of confusion. Measurement does not mean a person looking. It does not require consciousness, or awareness, or anyone taking notes. A measurement is any interaction that leaves a record in the wider world. A photon landing on a detector, an electron bumping into an air molecule, energy being deposited somewhere it can be traced. The universe was performing measurements for 13 billion years before there was anybody around to be confused by them. The rule that governs the outcomes is called the Born rule, published by Max Born in 1926. Quantum mechanics assigns each possibility a number called an amplitude, and the probability of that outcome is the square of the amplitude. It works to a precision no other rule in science approaches. Nobody knows why it is true. It was in fact added in a footnote. And there is a further process called decoherence, worked out by Dieter Zeh from around 1970 and developed by Wojciech Zurek afterwards, which explains beautifully why we never see a chair in two places at once. Contact with the surrounding environment spreads the delicate relationships out into the air and the light until they are no longer detectable in any practical way. Decoherence explains why superposition is invisible at our scale. It does not explain why one particular outcome happens rather than another. Those are different questions, and conflating them is the most common mistake in popular accounts of this subject. So I will say the honest version plainly. We can explain why you never see the strangeness. We cannot explain why you see one specific thing, which brings us to the uncomfortable domestic consequence. The floor beneath your bed, the water in the glass beside it, the atoms of the air you are breathing. None of these are made of small objects with definite properties, sitting there being themselves. They are made of things that acquire properties in the act of interacting, continuously, at an enormous rate, which is why the world looks as solid and settled as it does. Solidity is not a fact about the constituents. It is a statistic about how often they are being asked. So that is one die in the air with no face on it. Now take two of them, prepare them together, and let them go. There is a particular way of putting two particles together that has no equivalent anywhere in ordinary experience, and the trouble with describing it is that our language keeps offering us words that are slightly wrong. We say the particles are connected. They are not connected. There is no thread. We say they communicate. They do not communicate, and one of the firmest results in the field is that they cannot. We say they influence each other. That is closer, but it is exactly the claim that is in dispute. The one description that is accurate is also the one that sounds like a technicality, so I will say it carefully and then spend the rest of this section unpacking it. When two particles are entangled, there are not two descriptions, there is one. In quantum mechanics, the complete specification of a particle is called its state. Ordinarily, if you have two objects, you have two states. This one is doing this, that one is doing that. And the pair is described by putting the two descriptions side by side. Entanglement is the situation in which that is impossible. There is no description of the first particle on its own, and no description of the second particle on its own, that together reproduce what the pair actually does. The only complete description is of the pair as a single item. Ask what the first particle is doing, and the honest answer is that the question has no self-contained answer. The standard laboratory version works like this. Prepare two photons in a state that says, in effect, whatever polarization you find for one of these, the other will be at right angles to it. Notice what that statement leaves out. It does not say what polarization either photon has. It only pins down the relationship. The relationship is definite. The individual values are not there at all. That is the entire trick, and everything that follows in this story is a consequence of it. Now, how do you actually make such a thing? Because I want you to have the machinery in mind, not just the metaphor. The most common method is called spontaneous parametric down conversion, and it is more elegant than its name. You shine a laser at a particular kind of crystal, barium borate is a favorite, whose internal structure responds to light in a way that is not quite proportional. Almost all of the laser light passes straight through and nothing happens. But occasionally, roughly once in every 100 million or so photons, a single photon from the beam is converted inside the crystal into two photons, each with about half the original energy. Energy has to balance and momentum has to balance, which means the two new photons emerge along two cones of directions, precisely correlated. If you place your collection fibers where the cones intersect, you have no way of knowing which photon went which way, and that ignorance is not a limitation of your equipment. Because there is no fact about which is which, the pair emerges entangled. The apparatus fits on an optical bench. Undergraduates build them. There is a solid-state version too, which matters for the most important experiment in this story. A diamond is carbon, and occasionally the crystal contains a defect where a nitrogen atom sits next to an empty space where a carbon atom should be. That defect, called a nitrogen vacancy center, behaves like a single trapped atom held rigidly in place, and it can be prepared, manipulated with microwaves, and made to emit a photon whose properties are tied to the state of the defect. Send photons from two such defects in two separate laboratories to a beam splitter halfway between them, and arrange things so that when a detector clicks, you genuinely cannot tell which defect the photon came from, and the two defects, sitting in two different buildings, never having interacted, become entangled with each other. That procedure is called entanglement swapping, and it is how you build a pair whose halves have never been in the same room. What entanglement is not is at least as important as what it is. It is not a copy. The two particles do not carry duplicate information. Quantum states cannot be copied at all, which is a separate theorem with its own proof. It is not a signal, and we will spend a whole section later on exactly why not. And it is not the torn photograph. This is the distinction the entire video turns on, so let me put it as sharply as I can. In the photograph case, the two halves are different from the start. Sealing them in envelopes only hides which is which. In the entangled case, there is no equivalent of the two different halves. There is no moment at which one photon is vertical and the other horizontal, and the world simply has not told you. If there were, you would get different experimental numbers, and we know that because somebody worked out what those numbers would be. The other thing to know about entanglement is how fragile it is, because that fragility is the reason it took until the 1970s to see clearly, and the reason it will never be a household phenomenon. Entanglement survives only as long as the pair stays isolated. Any contact with anything else, an air molecule, a stray photon, the warmth of the apparatus, spreads the delicate relationship out into the environment, where it becomes, for practical purposes, unrecoverable. That is decoherence again, and its speed is extraordinary. A speck of dust floating in ordinary room air loses its quantum relationships in something on the order of a 10 billionth of a trillionth of a trillionth of a second. Move that same speck to the emptiness between the stars, with no air at all, and the faint background glow left over from the early universe is still enough to do the job in under a second. There is no natural setting anywhere in the universe where entanglement between everyday objects lasts. It is a condition that has to be built, defended, and used quickly. And it is used. This is not merely a curiosity kept in a drawer. Entangled pairs are the basis of quantum key distribution, in which two parties generate a shared secret whose secrecy is guaranteed not by mathematical difficulty, but by physics, because any attempt to intercept the pair disturbs it detectably. They are the basis of quantum teleportation, which does not move matter and does not exceed the speed of light, but does transfer the complete state of one particle onto another with the help of an ordinary message. They are the basis of the most sensitive measuring devices ever built. A Chinese satellite called Mikius distributed entangled photon pairs to ground stations more than 1,000 kilometers apart in 2017. Whatever this phenomenon is, it is now infrastructure. But here is the detail I want to leave you holding, because it is the one that will matter most, and it is the one the simple version of the story always leaves out. The dice always add to 7. In the real experiments, the correlation is not a single fixed relationship at a single fixed setting. You can choose the angle of your polarizing filter, Alice can choose the angle of hers, and there is a definite, predictable correlation between your results at every combination of angles, not just at the one where the numbers add to 7. When your angles match, the results are perfectly related. When your angles differ by a little, the results are strongly, but not perfectly related. When they differ by a lot, the relationship weakens in a specific, calculable way. That freedom to choose the angle is going to be the hinge of everything. Not because of what it lets you measure, but because of what it assumes about you. For now, notice only that the natural explanation is still standing. The particles agreed in advance. They carry instructions. The instructions cover every angle you might pick. It is a slightly more elaborate agreement than a number written on a card, but it is the same idea, and it is perfectly sensible. It was also the position of a man who spent 20 years insisting on it against the entire community of physicists, and who died believing he was right. On the 15th of May 1935, a paper appeared in the journal Physical Review, volume 47, page 777. Its authors were Albert Einstein, Boris Podolsky, and Nathan Rosen, and its title was a question: can quantum mechanical description of physical reality be considered complete? The answer the paper gives is no, and the argument it uses is so clean that it takes about 2 minutes to state. Suppose there is a quantity you can predict with certainty, without in any way disturbing the system it belongs to. Einstein, Podolsky, and Rosen proposed that if you can do that, then the quantity must correspond to something real that is genuinely out there. They called such a thing an element of physical reality, and the criterion is hard to argue with. If I can tell you, before anyone looks, exactly what a measurement on a distant object will give, and I have not touched that object, then it seems that the answer was sitting in the object waiting. Now apply that to an entangled pair. Measure your particle, and you can predict the distant one's result with certainty. You have not touched the distant one. It may be a mile away, or a light year. So by the criterion, the distant particle's property is an element of reality. It was there before you measured, but quantum mechanics does not include it. Quantum mechanics says the distant particle had no such property until the measurement occurred. Therefore, said the paper, quantum mechanics is not wrong, it is incomplete. There is more in the world than the theory describes, and one day we will find it. I want to be fair to Einstein here, because the caricature of him as an old man who could not keep up is both unkind and inaccurate. He never disputed that quantum mechanics made correct predictions. He had helped to build it. His 1905 paper on the photoelectric effect is one of its founding documents, and it is the work the Nobel Committee actually cited when they gave him the prize. His objection was narrower and more serious than stubbornness. He believed that a description which only ever gives probabilities cannot be the final description of a world in which particular things definitely happen. Something must decide which thing happens. If the theory does not contain that something, the theory is a summary rather than an account. The paper itself, oddly, annoyed him. Podolsky wrote the text, and Einstein complained afterwards in a letter to Schrödinger that the essential point had been buried under formalism. What he wanted to say was simpler. Either the two particles have their properties independently, or what you do here changes what is true there, and the second option is unacceptable. Niels Bohr, in Copenhagen, was reportedly thrown into some disarray by the paper and dropped everything to respond. His reply appeared in the same journal in October of the same year, under precisely the same title, and it is, by broad agreement including that of people who admired him enormously, close to impossible to follow. Bohr rewrote it repeatedly and remained dissatisfied. The physics community treated it as a victory anyway, largely because the alternative was to keep worrying, and quantum mechanics was busy being astonishingly successful at everything else. The person who read the EPR paper most carefully was Erwin Schrödinger, and it is to him that we owe the word. Writing later that year, he called the phenomenon Verschränkung, which in English became entanglement, and he did not describe it as one interesting feature among many. He called it the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought, not a trait. The trait. He also, in the same period, and in the same argument, produced the thought experiment about a cat in a box, which was not a celebration of quantum weirdness, but a complaint about it, a reduction to absurdity, meant to show that if you take the formalism literally, you end up with nonsense at ordinary scales. Einstein's own phrase for the alternative arrived 12 years later in a letter to his friend Max Born, dated the 3rd of March 1947. If the particles do not carry their properties with them, he wrote, then physics requires something he called spukhafte Fernwirkung, spooky action at a distance. He could not bring himself to believe in it. And there is the older remark from a letter to the same friend in 1926, which has become the most quoted sentence in the history of physics and is almost always quoted wrongly. Einstein wrote that the theory produces a good deal, but hardly brings us closer to the secret of the old one, and that he was at all events convinced that God does not play dice. It is not a religious statement. Einstein used that word to mean the deep order of nature, in the manner of Spinoza, whom he cited when asked. It is a claim that the universe is not fundamentally a lottery. Keep that sentence somewhere you can find it again, because by the end of tonight, it is going to mean something almost exactly opposite to what everybody thinks it means. And then, for 30 years, essentially nothing happened. This is the part of the story that surprises people. The question was not settled, it was set aside. Quantum mechanics was producing transistors and lasers and an understanding of chemistry, and the question of what the theory meant was quietly reclassified as philosophy, which in a physics department is not a compliment. Graduate students who asked what the wave function actually was were given a piece of advice that later got compressed into a slogan, "Shut up and calculate." That phrase was coined much later by David Mermin, but he was describing something real. Working on foundations was a career risk. Careers were damaged by it. John Clauser, whom we will meet shortly, was told by more than one senior figure that the experiment he wanted to run was a waste of a good physicist. There was also a more specific reason for the silence, and it is one of the stranger episodes in the history of science. In 1932, 3 years before the EPR paper, the mathematician John von Neumann published a rigorous treatment of quantum mechanics containing what looked like a proof that no theory of hidden instructions could ever reproduce quantum predictions. Von Neumann was one of the most formidable intellects of the century, and the proof was widely taken as final. If hidden variables were mathematically impossible, then Einstein was not merely unfashionable, he was refuted, and there was nothing left to discuss. The proof was wrong. It contained an assumption that no sensible hidden variable theory would satisfy, which meant it ruled out a class of theories nobody was proposing. What makes the episode remarkable is that this was noticed almost immediately. A young German mathematician named Greta Hermann published a paper identifying the flaw in 1935, the same year as EPR. Nobody read it. The proof continued to be cited as decisive for another 30 years, and it was only when Bell examined it in the 1960s that the error entered general circulation. Bell was blunt about it afterwards, saying the proof was not merely false but foolish, and expressing something close to anger that a generation had been discouraged by an argument nobody had checked. There was a second demonstration that the impossibility claim could not be right, and it was sitting in plain view. In 1952, David Bohm, an American physicist who had been driven out of the country during the anti-communist investigations and was working in Brazil, constructed a complete, working hidden variable theory that reproduced every prediction of quantum mechanics. It existed. It could be written down. Whatever von Neumann had proved impossible, Bohm had built. The reason for the wider paralysis, though, was not laziness and not the flawed proof alone. It was that nobody could see what to do. Einstein said, "The particles carry instructions." Bohr said they do not. Both pictures predicted exactly the same results in every experiment anyone could imagine, because both pictures had to reproduce the correlations that were already known. If two ideas make identical predictions about everything, then choosing between them is a matter of taste, and physics has no procedure for settling matters of taste. That is the situation as it stood for a generation, a disagreement about the nature of reality between the two most formidable minds of the century, universally agreed to be untestable, filed under philosophy, and left there. It was untestable because everybody knew it was untestable. Nobody had checked. John Stuart Bell was born in Belfast on the 28th of June, 1928, into a family that could not afford to keep him in school past 16. He got a job as a laboratory technician in the physics department at Queen's University Belfast, sweeping up and setting out equipment, and the staff there noticed him and let him attend lectures, and eventually he was admitted as a student. He took a degree in experimental physics, then another in mathematical physics, and ended up at the European Laboratory for Particle Physics near Geneva, designing accelerators. That was the day job, and he was very good at it. The work that made him one of the most important physicists of the 20th century was something he did on the side, and he described the split himself with a line that has outlived most of his technical papers. He said that he was a quantum engineer, but that on Sundays he had principles. In 1964, he took a year of unpaid leave and traveled to the United States, and while he was there, he wrote a 6-page paper called On the Einstein-Podolsky-Rosen Paradox. He sent it to a new journal called Physics, Physique, Physica, which published 4 volumes and then folded. He chose it because it paid its authors, and he had a year without a salary. The paper appeared on the 4th of November 1964 in Volume 1, pages 195 to 200. For several years, almost nobody read it. What Bell had done was to find a way to make Einstein's disagreement with Bohr into an experiment. The method is worth following, because everything in the second half of tonight depends on understanding what kind of argument it is. Bell did not devise a clever measurement. He devised a proof. He wrote down, in mathematical form, exactly what Einstein's picture claims, that the particles carry instructions, fixed at the source, covering every measurement that might be made on them. And then he asked what such a picture allows. Not what it predicts in one case. What it allows, at most, across every possible arrangement of instructions, including arrangements nobody would ever think of. And he found that it has a limit. There is a specific combination of measurements, whose results, added up in a specific way, produce a number, and no set of instructions carried by particles can make that number larger than a certain size. Any instructions at all, simple ones, complicated ones, instructions that depend on the weather. The ceiling holds for all of them. Quantum mechanics predicts a number above the ceiling. That was the achievement. 130 years of argument about whether the world contains hidden layers of reality had been converted into a quantity you could measure with a photon counter and read off a dial. Now, the argument rests on assumptions, as every proof does, and I am going to state them because we will be coming back to them. Bell assumed, first, that what happens at one detector does not depend on the setting of the other detector, when the two are far enough apart that no light-speed signal could get between them, that is locality. He assumed, second, that the particles carry definite instructions determining their behavior, some hidden set of properties we have not identified. That is the hidden variable picture itself, sometimes called realism. And he assumed, third, that the hidden properties carried by the particles are not correlated with the settings the experimenters choose, that whatever the photons are carrying has nothing to do with which angles get dialed in. 3 assumptions: locality, hidden instructions, and independence between the particles and the settings. From those 3, the ceiling follows. Let me give you a feeling for why the ceiling exists at all, because with the right example, you do not need any algebra. Imagine that instead of one measurement, you can make any of three at three different angles. Call them A, B, and C. You pick one at random. Alice, far away, picks one at random. Sometimes, you both pick the same one, and in that case, the results are always perfectly related. That is the 7, the part we already know. The interesting cases are when you pick different ones. If the particles carry instructions, then each particle arrived with an answer already written for all three questions. It might arrive carrying yes, yes, no, or yes, no, no. There are only 8 possible instruction sets, and every particle must have one of them. And here is the point. Whatever the instruction set is, it forces relationships between the different pairings. If a particle answers the same for A and B, and the same for B and C, it must answer the same for A and C. That is not physics. That is logic about lists. It holds for every one of the 8 possible lists, so it holds no matter how the instructions are distributed, no matter how cleverly. So when you tally up how often the different pairs of questions agree, the totals cannot fall into just any pattern. They are chained together. Quantum mechanics breaks the chain. It says that at certain angles, the agreement rates come out in a combination that no assignment of answers to all 3 questions can produce. Not an unlikely combination, an arithmetically impossible one, in the same way that no collection of people can contain more left-handed women than left-handed people. It helps to put real numbers on it, because the size of the discrepancy is part of what makes this so hard to argue away. Quantum mechanics says that if your filter and Alice's filter differ by an angle, the chance of your results disagreeing depends on that angle in a particular way, the square of the cosine of it. Line the filters up exactly, and you get perfect agreement. Set them 22.5 degrees apart, and the results disagree about 15% of the time. Double that separation to 45 degrees, and, if the world were built out of carried instructions, the disagreement rate could not possibly be more than twice the smaller figure, because disagreements can only ever add up. If the first pair disagrees 15% of the time, and the second pair disagrees 15% of the time, then the first and third can disagree at most 30% of the time. That is not a physical claim. It is bookkeeping, of the same kind that says a journey of 2 stages cannot be longer than the sum of the 2 stages. The measured figure at 45 degrees is 50%, not 30, 50. There is no arrangement of instructions, carried by anything, that produces that. The number that came to be used in the actual experiments is written S, and its ceiling under Einstein's picture is 2. Quantum mechanics predicts, at the best choice of angles, 2 times the square root of 2, which is about 2.8. That gap, the difference between 2 and 2.8, is where a century of argument lives. Bell's original inequality was not directly usable in a laboratory because it assumed perfect equipment and perfect correlations, and no real apparatus has either. In 1969, 4 physicists, John Clauser, Michael Horn, Abner Shimoni, and Richard Holt, published a generalized version in Physical Review Letters, Volume 23, page 880, which tolerates the imperfections of real detectors. It is universally known by their initials, and it is the form that every experiment since has actually measured. If Bell's paper was the proof, this was the blueprint. There is one more number worth knowing, because it raises a question nobody has answered. In 1980, the mathematician Boris Cyrulson proved that quantum mechanics cannot exceed 2.828 either. That is quantum mechanics' own ceiling, and you might assume that is simply where the ceilings run out. But it is not. If you ask what the maximum is for any theory at all that merely forbids sending messages faster than light, the answer is 4. There is room above quantum mechanics. Hypothetical devices that reach all the way to 4 have been studied. They are perfectly consistent, they do not permit signaling, and they do not exist. Nature climbs past the classical ceiling of 2, stops at 2.8, and declines to go further, and nobody knows what principle stops it there. It is worth being precise, at this early stage, about what a violation of the ceiling would actually establish, because this is the point where the popular version of the story starts to drift away from the mathematics. A violation would tell you that the three assumptions cannot all be true together. That is the whole of what it tells you. It does not identify the guilty one. A proof of the form, if A and B and C, then the number stays below 2, combined with a measurement showing the number above 2, gives you exactly one conclusion. At least one of A, B, and C is false. Which one is a separate question, and no measurement of the number can answer it, because the number is the same either way. Bell understood this perfectly, and said so repeatedly. He had come to the problem in the first place by reading Bohm's 1952 hidden variable theory, and what had struck him about it was not that it worked, but that it was violently non-local. The guiding wave in Bohm's theory reaches across any distance instantly. Bell's question was whether that non-locality was an unfortunate feature of Bohm's particular construction, or an unavoidable feature of any theory that reproduces quantum predictions. His theorem was the answer, and he regarded it as a discovery about nature rather than a refutation of Einstein. He thought the result showed something had to give. He was careful, throughout his life, about not overstating which thing. So by the end of the 1960s, the situation had changed completely. There was a proof. There was a testable form of the proof. There was a specific number, and two rival pictures of reality, predicting different values for it. What there was not, for 8 years, was anybody willing to build the machine. The senior figures in the field regarded the question as settled and the experiment as pointless, on the grounds that everyone already knew quantum mechanics would win. It fell to a young physicist who disagreed, who thought quantum mechanics would lose, and who wanted very much to prove it. The young physicist was John Clauser, and what makes him interesting is that he was on Einstein's side. Clauser had come across Bell's paper as a graduate student, at a time when almost nobody had, and his reaction was not that it settled anything, it was that somebody should actually go and look. He expected the experiment to show that quantum mechanics failed, that at the extremes, where nobody had ever checked, the theory would break down and Einstein's carried instructions would turn out to be there after all. He was warned off repeatedly. Senior physicists told him it was a waste of a career. He built it anyway, at Berkeley, with Stuart Friedman, using calcium atoms excited by ultraviolet light so that they dropped back down in 2 steps and emitted a pair of photons. The result appeared in Physical Review Letters, Volume 28, page 938, in 1972. The ceiling was exceeded by about 6 standard deviations. Quantum mechanics won, and Einstein's picture lost, and Clauser said afterwards that he was very sad about it. He had spent years building a machine to prove a point, and the machine had disproved him. 50 years later, he received the Nobel Prize for it. But the result did not settle the matter, and the reason is a word that is about to become the most important one in this story. The word is loophole. A loophole is not an error. It is an alternative explanation that a particular experiment happens to leave open. Bell's proof rules out carried instructions on the assumption that certain things are true of your apparatus, and if your apparatus does not quite meet those conditions, then a determined defender of carried instructions can say, "Your experiment is consistent with my picture too, and here is how." Every loophole has a name, and the 50 years after 1972 are the story of physicists building increasingly extraordinary machines to close them one at a time. The first loophole is called locality. In the Berkeley experiment, the angles of the polarizers were set by hand before the run and left there. That means the source of the photons, in principle, could have known what the settings were going to be. Perhaps a photon emitted by a calcium atom somehow senses the orientation of a filter 3 meters away and adjusts itself accordingly, by some ordinary mechanism nobody has thought of. It sounds far-fetched. It is also not ruled out, and in this business, you do not get to dismiss things because they sound far-fetched. Closing it requires choosing the settings so late that no signal traveling at the speed of light could carry the choice to the source in time. That is what Alain Aspect built, in a basement at Orsay, outside Paris, and it is worth standing in that room for a moment. It is 1982. The apparatus runs the length of the laboratory, about 13 meters from one detector to the other, and along each arm there is a small vessel of water with an ultrasonic transducer in it. The transducer is vibrating at close to 50 megahertz, setting up a standing wave in the water that acts as a mirror, and then, a fraction of a moment later, does not, so that a photon arriving at that point is deflected toward one polarizer, or a different one, and which one it goes to changes every 10 nanoseconds. Light takes about 43 nanoseconds to cross the apparatus. So by the time a photon reaches the switch, the choice that will be made about it has not yet been made, and by the time the choice is made, there is no way to inform the other end. The two transducers run at slightly different frequencies, deliberately, so that they cannot fall into step. There is a low hum in the room. The coincidence counter accumulates through the night, and the number climbs, past 2, into territory where no instruction carried from the source can follow it, while nothing in the room appears to be doing anything at all. Aspect had gone to Geneva before building it, to describe the plan to Bell in person. Bell's first question was whether he had a permanent position. Aspect said he did not. Bell told him he must be a very courageous graduate student, because a negative result would end his career and a positive result would only confirm what everyone already believed. The result, published in Physical Review Letters, Volume 49, page 1804, exceeded the ceiling by 5 standard deviations. In particle physics, 5 standard deviations is the conventional threshold for calling something a discovery. The second loophole is called detection, or fair sampling, and it is more insidious. Photon detectors are inefficient. In 1982, the overwhelming majority of the photons produced were never registered at all. The experiment saw perhaps 1 in 100. So the tally is not a tally of everything that happened. It is a tally of what got caught. And if the photons that get caught are not a fair sample of the photons that exist, if some property of a photon makes it slightly more likely to be detected in one configuration than another, then the correlation you measure could be an artifact of the sampling rather than a fact about nature. Closing this one is not a matter of cleverness. It is a matter of building detectors good enough, and the threshold is brutal. You need to catch roughly 2/3 of everything, end to end, including every lens and every fiber and every connector. That took 30 years and a new technology, superconducting nanowires, cooled to under a degree above absolute zero, which register a single photon by the tiny burst of heat it deposits. There is a third loophole, subtler than either, called the coincidence time loophole. When you are catching individual photons at 2 distant stations, you have to decide which detection at one station belongs with which detection at the other, and you do that by matching up their arrival times within a small window. That matching is a choice made by the experimenter after the fact, and it turns out that a hidden variable model in which the emission times themselves depend on the detector settings can manufacture apparent violations purely out of how the pairs are matched. It is a genuinely sneaky possibility, and closing it requires either fixed time slots decided in advance or an event-ready scheme where a third party announces the pair before the measurements happen. Between Orsay and 2015, there was an intermediate step that deserves a mention. In 1998, in Innsbruck, Gregor Weiss and Anton Zeilinger repeated the locality closure properly, with the two stations 400 meters apart across the university campus, and the settings chosen not by a periodic vibrating mirror, but by fast physical random number generators, making a fresh decision for each photon. Aspect switches had been periodic, which meant that in principle their pattern was predictable in advance, and Aspect himself had said so in print. Innsbruck removed that objection, and it is the experiment that established the modern template: independent random choices, made late, at both ends. Everything came together in 2015, in 3 laboratories, independently, within months of each other. In Delft, in the Netherlands, Bas Hensen and colleagues used the diamond defects we met earlier, in 2 laboratories 1.3 kilometers apart, across the university campus, with a third station in the middle. Their scheme was event-ready, the middle station announced when a pair had genuinely been established, so there was no question of selecting which events to count. The rate was appalling. They collected 245 valid trials over 18 days, roughly 1 event per hour of running. The result appeared in Nature, volume 526, and it closed the locality and detection loopholes at the same time, for the first time in history. In Vienna, Marissa Justina and colleagues did it with photons and the new superconducting detectors, in Physical Review Letters, volume 115, page 250401. Their statistics were on a different scale entirely. The probability that their result could have arisen from a world of carried instructions and coincidence came out around 3 in 10 million trillion, a decimal point, followed by 30 zeros and then a 3. Numbers like that are meaningless unless you tie them to something. Here is one way to hold it. If you took every second that has elapsed since the universe began and picked one of them at random and then did it again and required both picks to land on the same specified second, that would still be a more likely accident than this result being a fluke. At the National Institute of Standards and Technology in Boulder, Colorado, Lyndon Shalm and colleagues published their own version in the same journal and the same month. 7 years later, on the 4th of October 2022, the Royal Swedish Academy of Sciences announced that the Nobel Prize in Physics would go to Alan Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. 10 million Swedish krona, split 3 ways. The man who had built his machine hoping to prove quantum mechanics wrong collected a third of it. And that is where the story is usually told to end. Einstein was wrong. The particles do not carry instructions. Reality, in the phrase that went round the world that week, is not locally real. Everything in that summary is defensible, but it is a summary of a conclusion, and it is not quite a summary of what was proven, and the space between those two things is where the rest of tonight is going to happen. Let us step back and put the pieces together, because we are halfway through, and the shape of the thing is about to change. We started with a pair of dice that always add to 7, each one individually random, perfectly coordinated, across any distance. We found that the quantum version is real and manufactured routinely. We looked at what a single quantum object is doing before measurement, and found that the honest answer is that it has no value to be found. We looked at how a pair is prepared, so that only the relationship is definite, and neither member has a property of its own. We met Einstein, who said that this cannot be the whole story, and that the particles must be carrying something. We met Bell, who turned that disagreement into a number with a ceiling. And we followed 60 years of experiments in which the ceiling was exceeded again and again, in ever more carefully sealed conditions, until in 2015, 3 laboratories closed the last serious technical objections simultaneously, and in 2022, the work was given the Nobel Prize. The conclusion everybody draws from that is, Einstein was wrong. Reality is not locally real. Now I want to look very carefully at the logic that gets us from the measurement to the conclusion, because it is not quite what it appears to be, and once you see it, you cannot unsee it. Bell's theorem is not a statement about the world. It is a conditional. It has the form, if these things are true, then this number cannot exceed 2. That is what a proof is. It takes premises in and produces a consequence out, and the consequence is only as good as the premises. The experiments tell us the number exceeds 2. Combine that with the theorem, and you get exactly one conclusion, delivered by logic, with no room for interpretation. At least one of the premises is false. That is all. That is the entire content of the experimental result. It does not tell you which premise. It cannot tell you which premise, because the number is the same regardless of which one fails. Every one of those beautiful machines, every superconducting detector, every 18-day run collecting 245 events, 1 per hour, all of them measure the same quantity, and that quantity is silent on the question of which assumption to abandon. So we had better look at the list again. Earlier I stated it, deliberately without emphasis, and if you were not listening closely, you will have heard 2 items where there were 3. The first premise is locality. What happens at your detector does not depend on the setting Alice chose. When the 2 of you are separated far enough that no light-speed signal can cross between the choice and the outcome. The second premise is that the particles carry definite properties, the hidden instructions, the thing Einstein wanted, sometimes just called realism. And the third premise is this: the hidden properties carried by the particles are uncorrelated with the settings that the experimenters choose. Read that third one again. It does not say anything about faster-than-light influence. It does not say anything about whether properties are real. It is a statement about the relationship between 2 things, what the particles are carrying and what the humans dial in. And it says, there is no relationship. Whatever the photon has got, it has nothing to do with the angle you are about to select. The 2 are independent. If that premise is false, the theorem does not go through, not weakened, not harder to violate. The derivation cannot be performed at all. Every step of Bell's proof uses that independence, and without it, there is no ceiling of 2, and a world with perfectly ordinary local physics and perfectly ordinary carried instructions can produce every correlation ever measured, including the ones at 45 degrees, including the ones with p-values of 1 in 10 to the 31. I want to be precise about how strange this situation is, because it is easy to hear it as a technicality. That premise is in Bell's original 1964 paper. It is in every textbook derivation of the inequality that has ever been written. It is discussed in the Nobel Committee's own scientific background document. It is not hidden, and nobody has concealed it. But it is almost never mentioned when the result is explained to the public. And the reason it is not mentioned is that it seems too obvious to be worth stating. Of course, the photon does not know which angle I am going to pick. What would that even mean? And that reaction, of course, obviously, what would that even mean, is doing an enormous amount of work. It is not an experimental result. Nobody has ever tested it. As we will see shortly, nobody can. There is a particular feeling that arrives at this point, and I think it is worth naming, because it is not the feeling of learning a new fact. It is the feeling of finding out that something you were standing on is a lid. For the last hour, you have been carried along a story with a very satisfying shape. A great physicist made an objection. A brilliant argument turned the objection into an experiment. The experiment was performed with increasing care for 50 years, and the objection was defeated. That story is true. Every event in it happened. The prize was awarded, the papers exist, the p-values are real. What is not quite true is the moral, and the moral is the only part most people ever hear. Nobody lied about this. There was no cover-up, and no conspiracy of silence. The premise is written down in the original paper, in the textbooks, in the official Nobel documentation. It is simply that when a result is passed along, from the journal to the press release, from the press release to the article, from the article to the conversation, the parts that feel obvious fall away first. And this part felt obvious to everyone, for 60 years, including to almost every physicist who repeated it. The structure here is the ordinary structure of a proof by contradiction, and it is worth having the shape of it in mind. Imagine a detective who says, if the door was locked and the window was sealed and the housekeeper had no key, then nobody could have entered. Somebody entered. What follows is that one of those three things is false. What does not follow is that the window was open. You cannot get to the window from that argument alone. You need a separate reason to look there, and if you have spent the whole investigation assuming the housekeeper is beyond suspicion, you will find yourself very confident about the window without ever having earned it. So here is where we actually stand. 60 years and one Nobel Prize after the question was made testable. There are three things on the table. Logic says at least one of them is false. The experiments have not told us which. And the popular account of what was discovered presents the choice as being between the first two, because the third was quietly assumed to be beyond dispute before the argument started. Which one do you delete? That is the question the rest of this video is about, and I am not going to answer it yet, because the answer only means something once you have seen why the two comfortable options do not work. We are still not ready. But before we can take the third premise seriously, we have to deal with the thing everybody reaches for first. The idea that something simply travels between the particles, very fast, and that this is the whole explanation. It is the most natural thought in the world. It is also the one option that can be ruled out completely. The instinct is almost impossible to resist. If the two particles are coordinated, and they did not agree beforehand, then something must pass between them at the moment of measurement. A nudge, a note, something. So let us take that seriously and ask the obvious follow-up question, how fast would it have to go? This has actually been measured after a fashion. In 2013, a group in China, led by Huan Yin, ran a Bell test with an ingenious twist. They arranged the two measurement stations so that, from the point of view of a particular moving reference frame, each measurement happened before the other. Which sounds like nonsense until you remember that in relativity, the order of two distant events genuinely depends on who is asking. By analyzing the timing very carefully, they were able to set a lower limit on how fast a hypothetical influence would have to travel to keep the two results in step. The number they got was about 10,000 times the speed of light. You will see that figure quoted, and it is almost always quoted as though it were a measurement of the speed of entanglement. It is not. It is a flaw. It says, if something travels, it travels at least this fast. It does not say anything travels, and the awkward feature of a flaw is that it moves. Every improvement in timing precision raises it, and it has been raised repeatedly, and there is no experiment in prospect that would ever land on a value. The number does not converge on an answer. It runs away from zero forever. There is a much deeper problem with the traveling influence picture, and it is the reason physicists do not take it seriously, even as a possibility. You cannot use it, ever. Not with better equipment, not with cleverer coding, not in principle. Here is why, and it is worth doing slowly, because this is the point where most explanations of entanglement quietly go wrong. Suppose you want to send Alice a message. You have your particle in Las Vegas. She has hers in Macau. You measure yours, and you get a result. But you did not choose that result. You cannot choose it. The outcome you get is random, and it is random in a way you have no handle on whatsoever. You cannot bias it, nudge it, or select it. All you can do is measure and see what comes out. Meanwhile, Alice measures hers and gets a result that is also, from her side, completely random. She sees a string of outcomes that looks exactly like a coin flip sequence. Nothing you do, measuring early, measuring late, not measuring at all, changing your angle, smashing your apparatus with a hammer, makes any detectable difference to what she sees. Her statistics are identical in every case. The relationship between your results and hers is real, but it is invisible from either side alone. It only appears when the two lists of outcomes are put next to each other, and putting them next to each other requires one of you to send the other a list, by telephone, by email, by letter, by any ordinary means, all of which crawl along at or below the speed of light. It is worth trying to break this, because most people's first instinct is that there must be a way around it. So let us try. You cannot control your outcome, but you can control your angle, so encode the message in the angle. Agree in advance that if you set your filter vertical, that means yes, and if you set it at 45 degrees, that means no. Now Alice, 7,000 miles away, measures her particles and looks at her results to work out which you chose. She cannot. Her results are an even split between her two possible outcomes, whichever angle you picked. That is not a coincidence, and it is not approximate. It is exact, and it holds for every angle you might choose and every state you might prepare. The correlation between your list and hers changes when you change your angle, but the correlation is not visible in her list. It only exists in the comparison. She would need your list to see it, and your list has to travel. Try it with 1,000 pairs, hoping to see a statistical fingerprint, and the fingerprint is not there. Try it by measuring yours first, or hers first, and the answer does not change, which is fortunate, because in relativity, there is no universal fact about which of you went first. This is not a practical limitation waiting for better technology. It is a theorem, and it follows directly from the mathematical structure of quantum mechanics. It is called the no communication theorem, and it was proved rigorously in 1980. Entanglement cannot carry information. What it can do is guarantee that two records, made independently and far apart, will match in a way that no set of carried instructions could have arranged. But you only ever find that out afterwards, in the ordinary way, at ordinary speed. Nobody had to be told anything, and nobody could have been told anything. I should say what the real technology is, because it gets confused with this constantly. Quantum key distribution is genuine, deployed, and commercially available. Two parties share entangled pairs and use them to generate a string of random bits that they both possess and nobody else does. And if an eavesdropper interferes with the pairs, the interference shows up in the statistics, and the parties know to throw the key away. It is a beautiful application. But the key is random. It is not a message. The message still has to be sent afterwards, encrypted with that key, down an ordinary fiber, at the ordinary speed. And there is a final reason to be glad of all this, which is that the alternative would be worse than you might think. Faster than light signaling does not merely violate relativity as a matter of bookkeeping. In relativity, whether two distant events happen at the same time depends on your state of motion. This is not a philosophical claim. It is measured daily in particle accelerators and satellite clocks. If a signal can outrun light, then there exist observers, in perfectly ordinary states of motion, for whom that signal arrives before it was sent. Chain two such signals together, in opposite directions, and you can send a message into your own past. You could tell yourself not to send it. There is no version of physics that survives that, which is why even a signal traveling 5 miles an hour faster than light would be a catastrophe rather than a curiosity. This is also the right place to close a set of claims that circulate widely, because I would rather address them than pretend they are not out there. Entanglement is used, in a great deal of popular material, to explain things it has nothing to do with: telepathy, healing at a distance. The idea that two people who care about each other are entangled, or that intentions can be transmitted, or that the universe responds to focused thought because of quantum connection. I want to be respectful about this, because the impulse behind it is a real and decent one. People are reaching for a physics that makes the world feel less lonely. But the physics does not say this. Entanglement between two large warm objects does not survive contact with the world for any measurable length of time. A speck of dust in ordinary air loses it in a fraction of a second, so small it has no useful name. And even if two particles inside two people were entangled, the no communication theorem would still stand between them and any message. Nothing gets through. That is not a gap in our knowledge. It is one of the very few things here that is fully settled. So the escape route is closed. No agreement was carried. The experiments rule that out. No signal was sent. The theory rules that out. And the universe would fall apart if it were otherwise. Which leaves the third premise, the one about you. The third premise has several names, and the names are revealing, because each one was chosen by somebody with a slightly different attitude to it. The technical name is statistical independence. In the mathematics, it is a single short line saying that the distribution of the hidden properties does not depend on the detector settings, that if you sorted all the particle pairs in the universe by what they were carrying, the sorting would come out the same whichever angles happened to get chosen. Some authors call it measurement independence, which says the same thing from the other end. Some call it the freedom of choice assumption, which is the version you will see in the experimental papers, and which quietly imports a claim about experimenters as well as about particles. And the oldest and bluntest name, the one used when people are arguing rather than publishing, is the no conspiracy assumption. In plain speech, all four names mean this: whatever the photon is carrying has nothing to do with which angle you are going to select. Now, I said earlier that if this premise fails, Bell's proof does not go through. I want to be precise about how badly it fails, because the usual assumption is that a violation of this premise would make the inequality slightly harder to violate, or would require a slightly strained explanation, and that is not the situation. Without statistical independence, there is no inequality, there is no ceiling of 2. The derivation cannot be performed at all, because the very first step involves averaging over the hidden properties in a way that treats them as unrelated to the settings, and if they are related, that average is not the quantity Bell computes. What you are left with is a world in which particles carry ordinary instructions, in which nothing travels faster than light, in which there is exactly one universe and no branching, in which nothing collapses, and in which every correlation that has ever been measured comes out exactly as observed. Every one, the 45-degree result, the 9.3 standard deviations, the 1 in 10 to the 31. That is a startling amount of power to be sitting inside a premise that nobody remembers is there. So why did Bell include it? Because he was careful. He knew that a theorem is only as strong as what it assumes, and he wanted the assumptions written down. He came back to it more than once. In a note from 1977 called Free Variables and Local Causality, he examined the question of whether the settings could be treated as free, and concluded that this is something we assume in ordinary experimental practice and cannot prove. He did not hide it. He put it on the record, and then the record was not read. Which brings us to the interesting question. If this premise is unproven, untested, and load-bearing, why does essentially the entire field treat it as beyond discussion? The answer, when you go looking, is almost never a citation. It is a word. The word is conspiracy. The idea is that for the third premise to fail, the universe would have to be arranging something, coordinating the photon's hidden state with the experimenter's choice, in a way that looks deliberate. It feels like being deceived. It feels like nature going to some trouble to fool us, which is the one thing scientists are trained above all else to be suspicious of. But look closely at what that objection is actually made of. Conspiracy is a claim about intention. It requires somebody to be arranging things. And there is nothing in the mathematics that mentions intent, or arrangement, or deception. What the mathematics says is that two quantities are correlated. That is all. And correlation between two distant quantities is, in every other branch of physics, the least remarkable thing in the world. Indeed, it is the first thing we look for, because it usually means the two things share a history. Consider how routinely we accept this elsewhere. If you measure the temperature of the microwave background in one patch of sky and in another patch on the opposite side, you find them matching to a few parts in 100,000. Two regions that have never been in contact, in the ordinary sense, agreeing to extraordinary precision. Nobody calls that a conspiracy. Cosmologists call it a clue, and they built an entire theory, inflation, to explain it. Precisely by giving the two regions a shared past. Common cause correlation is not an exotic hypothesis. It is the ordinary explanation for almost everything. And here is the thing about the photons and the settings. They do share a past. Everything does. The photon was made in a crystal, and the crystal was made by a company, and the laser was built by engineers, and the experimenter is a physical object made of atoms that were forged in stars, and if you run the whole system backwards far enough, every component of the experiment, the particles, the apparatus, the random number generator, the brain of the person watching, occupies the same past light cone. They are not independent systems that happen to be in the same room. They are pieces of one connected physical history that has been evolving under one set of laws. Whether that shared history produces the specific correlation required is a completely open question. Nobody has shown that it does. But the objection that it would be a conspiracy is not an argument that it does not. It is an aesthetic reaction, and it is worth noticing that the same field which finds this unbearable is entirely comfortable with alternatives that are, by any ordinary standard, more extravagant. If you would rather say that every measurement splits the universe into branches that can never be observed, or that there is a guiding wave stretching across the cosmos that updates instantaneously and needs a preferred definition of now that relativity says does not exist, those are respectable positions, held by serious people, taught in courses. Correlation from a shared past is the one that gets called a conspiracy. There is also a question of scale that almost never gets asked, and asking it changes how the objection feels. When people imagine a violation of statistical independence, they picture something enormous, the entire universe conspiring, every particle everywhere coordinated for all time, a cosmic stage management operation of unimaginable scope. But that is not what the mathematics requires. What is required is a correlation between two specific things, in one small region, over a short interval, what a particular pair of photons is carrying, and what a particular pair of detectors is about to be set to. It does not have to hold across the galaxy. It does not have to hold across the century. It has to hold in the few meters and few microseconds between the crystal and the filters, and the amount of correlation required is small. This is a technical point that the defenders of the idea have been making for years, and it is not intuitive. You do not need the settings to determine the hidden variables or anything close to it. You need a slight statistical lean, a correlation far too weak to notice in any single run, far too weak to let you predict anything, but enough that the averaging step in Bell's proof is not valid. The picture of the universe as a puppeteer arranging every detail is not the hypothesis. The hypothesis is that two physical systems in contact with the same past are very slightly not independent, which is the default expectation for physical systems in every other context we have ever examined. There is one further feature of this premise that is easy to miss, and, once you see it, is genuinely unsettling. Any experiment you might design to test whether the settings are independent of the hidden variables would itself involve choosing settings. You would need to establish that your test settings were independent, and to do that, you would need another test, whose settings would also need establishing. The assumption cannot be checked from the inside, because the checking uses it. It is not that we have not got round to it. It is that the tool required to examine the assumption is the assumption. There is a piece of mathematics that makes the stakes here very clear, and it has a provocative name. In 2006, and again in a strengthened version in 2009, the mathematicians John Conway and Simon Cochin published what they called the free will theorem. It says, roughly, that if the experimenters have free will, in the specific technical sense that their choices are not determined by anything in the past of the experiment, then the particles must have the same kind of freedom, and their responses cannot be functions of any prior state of the universe. It was presented as a surprising result about particles. But every theorem can be read backwards, and read backwards, it says something else. If the particle's behavior is determined by the past, then the experimenter's choices are too. You do not get to have one without the other. They are the same assumption. There is a second, less famous constraint worth mentioning in passing. In 1967, Simon Cochin and Ernst Specker proved something independent of Bell, that you cannot consistently assign pre-existing values to all the quantities of a quantum system in a way that does not depend on what else you choose to measure alongside them. The value you get is tied to the context of the question. That result also assumes the experimenter's choice of context is free. Everything in this area does. So we arrive at a rather remarkable place. Physics has performed some of the most delicate and expensive experiments in its history to close the loopholes in Bell's theorem. Locality, closed. Detection efficiency, closed. Coincidence timing, closed. And the third premise, which is just as necessary to the conclusion as the other two, has never been the subject of a single dedicated experiment designed to detect its violation. Not one, in 60 years. There are two possible reasons for that. Either nobody thought it was worth doing, or it cannot be done. It is the second one, and the experiment that comes closest to trying is, by a wide margin, the most beautiful thing in this entire story. If you cannot prove that the experimenter's choice is independent of the particles, there is one thing you can do instead. You can take the choice away from the experimenter and hand it to something that could not plausibly have been in on it. That is the idea behind a family of experiments that are, to my mind, the most inventive thing anybody has done in a laboratory in the last 20 years, and their entire purpose is to attack the one loophole that cannot be closed. The first serious attempt came in 2010 from a group led by Thomas Scheidel, working with Anton Zeilinger in the Canary Islands, sending entangled photons between La Palma and Tenerife, and arranging for the setting choices to be made by random number generators, positioned so that no signal from either choice could reach the source before the pair was created. It was a real advance, but it has a limit. A random number generator is a physical device, sitting in the same laboratory, made of the same kind of matter, and if the third premise fails at the level of physical law, a box of electronics is no more independent than a coin. So the next step was to reach further away, much further. In 2017, Johannes Hansteiner and colleagues in Vienna built a version in which the detector settings were not generated locally at all. They pointed two small telescopes at two different stars, several hundred light-years away, and measured the color of the arriving starlight. Red meant one setting, blue meant the other. The decision that determined how each photon would be measured was therefore made by light that had left its star roughly 600 years ago, before Columbus sailed, and had been traveling ever since. If anything in the experiment's neighborhood was correlating settings with particles, it had to have been doing so for 6 centuries. And then they went further still. It is 2018, on a ridge on the island of La Palma, well above the cloud layer, where the observatories sit because the air is thin and steady. 2 telescopes are trained on 2 points of light that are not stars. They are quasars, the incandescent regions around supermassive black holes in the centers of distant galaxies, the brightest sustained objects the universe produces. One of them is far enough away that its light has been traveling for roughly 7.8 billion years. It left before the Earth existed. It left before the Sun existed. It has been crossing an expanding universe for more than half the age of everything. And tonight, it ends its journey by falling into a small detector, having its wavelength measured in a few millionths of a second, and setting the angle of a polarizing filter for 1 photon in an experiment being run by a species that had not yet appeared when the light departed. Down in the laboratory, entangled pairs are being produced and sent to the 2 stations. Each one is measured at an angle chosen by an ancient photon. The counters accumulate through the night, and the number climbs past 2 again, to a violation of 9.3 standard deviations, with a probability of arising by chance of roughly 7 in 100 billion. The paper, published in Physical Review Letters, put the achievement in a way that is worth quoting almost exactly. The experiment pushed back to at least 7.8 billion years ago, the most recent moment at which any local realist mechanism could have exploited the freedom of choice loophole, and it excluded such mechanisms from 96% of the space-time volume of the experiment's past light cone. That sentence deserves unpacking, because it contains both the triumph and the defeat. Your past light cone is the set of all events that could possibly have influenced you. Everything close enough in space and far enough back in time that a signal at light speed could have got from there to here. It is the complete list of things that are allowed to be causes of you. What the quasar experiment did was to take that entire region of the universe's history and rule out 96% of it as a possible home for whatever might be correlating settings with particles. 96% sounds like a rout. It is not. And the reason is geometric. The volume of a light cone does not grow steadily with time. It grows as roughly the 4th power of time, which means that the remaining 4% is not a thin sliver at the edges. It is the earliest portion, the beginning, the part closest to the origin of everything, the part from which every subsequent thing descends. The experiment ruled out almost the entire recent history of the universe, and left untouched precisely the era from which all common causes would have to come anyway. Here is a way to feel the geometry. Imagine the past of the universe as a cone widening upward from a point, with you at the top. Slice off the top 96% of its volume, and what remains at the bottom is not a trace amount left over from a nearly complete job. It is the narrow beginning, the era of the first few 100 million years, and behind that, the era of the first minutes, and behind that, the era in which everything we now see was in causal contact with everything else. If you were going to look anywhere for a common cause linking 2 things that seem unrelated, that is the only place worth looking, and it is the exact region that survives. The details of the 2018 run are worth having, because they show how hard the team worked to make the 2 ends independent. The 2 telescopes were pointed at different quasars in different parts of the sky, one whose light had been traveling roughly 7.8 billion years and one at roughly 3.9 billion. Different objects, different distances, different directions, so that no single event in the sky's past could have set both. The color measurement and the switching of the polarizer had to be completed in a few microseconds before the entangled photons arrived, and the whole chain ran automatically through the night while the astronomers watched the counts. And it can never do better. That is the part that stops the argument. There is no telescope that can look outside the universe's own causal history, because there is nothing outside it to look at. Any object you point at is, by definition, inside your past light cone. That is what it means for its light to have reached you. You can push the correlation back 1,000 years, or 8 billion, or 13.8 billion minus an instant, and the loophole simply moves back with you and waits. The 4% cannot be reduced to zero by any instrument that has ever been imagined, because the obstacle is not a limitation of engineering, it is the shape of causality. The people who did this work know it perfectly well and say so. The papers describe themselves as pushing the loophole back, not closing it. That framing is right there in the abstracts. It is one of the more honest things in modern physics, and it is almost never repeated when the results are described elsewhere. There was one more attempt, and it took a completely different approach, and I love it for its sheer optimism. On the 30th of November, 2016, more than 100,000 people around the world sat down at computers and played a small online game. The game asked them to press keys in an unpredictable sequence, and the keystrokes were converted into bits and routed live, over the internet, to 12 laboratories on 5 continents, running 13 separate experiments on photons, on single atoms, on clouds of atoms, on superconducting circuits. In a single day, the participants generated 97,347,490 binary choices, and every one of them was used to set a detector somewhere in the world. It was called the Big Bell Test, and the results were published in Nature in May 2018. The idea was that if you are worried the settings might not be free, use the freest thing you can find, 100,000 human beings deciding. And this is the moment where the whole campaign runs into the wall, because that argument only works if human beings are outside the physics. If the third premise fails as a matter of physical law, if the correlation between hidden states and settings is something the laws simply do, then it applies to the sodium and potassium ions crossing the membranes of 100,000 human neurons exactly as it applies to a random number generator or to a quasar. A law does not check what kind of object it is acting on. Using people instead of electronics closes the loophole only if people are exempt from the laws that would create it, and if we knew that, we would not need the experiment. So this is the position. The most ingenious loophole-closing campaign in the history of experimental physics has been run against this premise for 15 years by some of the best people in the field, using starlight, quasars, satellites, and 100,000 volunteers, and it has established with certainty that the correlation, if it exists, was not arranged recently. That is genuinely all it can establish, and the people who ran it said so at the time. Some questions stay open because we lack the instrument. This one stays open because of the structure of cause and effect. And the theory that lives in that remaining 4% has a name. The man who gave it that name understood it more clearly than anyone who has defended it since, and he spent the rest of his life hoping it was wrong. The name is superdeterminism. In 1985, John Bell sat down for a radio interview with the physicist Paul Davies, later printed in a collection called The Ghost in the Atom, and he was asked about the implications of his own theorem. What he said in reply is the clearest statement of the idea anyone has ever made, and it has been sitting in print for 40 years. He said that there is a way to escape the inference of superluminal speeds and spooky action at a distance. But, he said, it involves absolute determinism in the universe, the complete absence of free will. Suppose the world is superdeterministic, he said, with not just inanimate nature running on behind-the-scenes clockwork, but with our behavior, including our belief that we are free to choose to do one experiment rather than another, absolutely predetermined. Then, he said, the difficulty disappears. There is no need for a faster-than-light signal to tell particle A what measurement has been carried out on particle B, because the universe, including particle A, already knows what that measurement and its outcome will be. Read that carefully, because it is doing something remarkable. The man who proved that Einstein's picture cannot survive is explaining, precisely, the one condition under which Einstein's picture survives entirely intact. I want to be exact about what Bell did and did not do here, because it is often reported carelessly, including in the material that prompted this video. Bell did not propose superdeterminism. He identified it. He described it more clearly than most of the people who have since defended it, and then he declined to take it, and he was open about his reasons. His objection was not that it had been refuted, it was that he found the world it implies almost impossible to work in. If the experimenter's choices are not free, he wrote elsewhere, then it becomes difficult to see how one could do science at all, because the whole method of science is to vary one thing and see what happens, and that method presumes the varying is not itself part of what you are studying. He named the exit and stood in front of it for the rest of his life. Now let me draw the distinction that everything depends on, because superdeterminism is constantly confused with plain determinism, and they are not the same thing at all. Determinism is the ordinary claim that the state of the world at one moment fixes the state at the next. Newton's mechanics is deterministic. So, importantly, is Bohm's pilot wave version of quantum mechanics. It has definite particles following definite trajectories, no randomness anywhere, everything fixed. And Bohm's theory does not violate the third premise, which is exactly why it is forced to be violently non-local. The guiding wave has to reach across space instantaneously, because if the settings really are independent of the particles, then something has to do the coordinating, and there is nothing else left. So the relationship is this: determinism plus independence between particles and settings gives you a theory that must be non-local. Determinism minus that independence gives you superdeterminism, which is local. The entire difference between the two is that one small premise, and every strange thing anybody has ever said about quantum mechanics being non-local, is downstream of which side of it you stand on. What would a superdeterministic universe actually be like? It is worth describing carefully, because it is not what most people imagine when they hear the word. Nothing travels faster than light. Nothing collapses. Nothing splits into branches. There is exactly one world, and it is local, in the strict sense that what happens here is affected only by what is in the immediate neighborhood of here. Particles have definite properties at all times. The wave function is not a physical object at all. It is a bookkeeping device, a summary of what can be predicted given what is known, in the same way that a weather forecast is not a thing in the sky. And the randomness of quantum measurement is not fundamental. It is the appearance produced by hidden degrees of freedom that we cannot see and cannot control, in exactly the way that a coin toss looks random to a person and does not look random to the physics. In that world, the entangled pair is not doing anything mysterious. Your die was always going to show a 2. Alice's was always going to show a 5. And the reason your choice of angle did not spoil the arrangement is that your choice was never a free variable to begin with. It was another part of the same physical system, evolving under the same law, correlated with the rest of it through their shared past. Nobody had to be told anything, because nothing was ever undecided. That is the sentence the whole video has been walking towards. Earlier, when we closed the door on faster-than-light signaling, that same phrase was a frustration. Nobody could be told anything, so the comfortable explanation was unavailable. Here it turns over and becomes the answer. Nobody had to be told anything, because there was never a moment when anything was waiting to find out. Now, who actually holds this position? Because it matters that the answer is not nobody. The most senior figure is Gerard Hooft, who shared the 1999 Nobel Prize in Physics for work on the structure of the electroweak interaction, which is about as far from the fringe as a person can stand. For more than 2 decades, he has argued that quantum mechanics is not the bottom layer, that underneath it is a deterministic system, something like a cellular automaton, a lattice of simple states updating according to simple rules at or near the smallest scale physics allows. His book on this, published open access in 2016, contains chapters titled, in so many words, Entanglement and Superdeterminism and the Rejection of Free Will. His central move is elegant. He proposes that only certain states, which he calls ontological states, are physically real, and that superpositions of them are descriptions of our ignorance rather than physical situations. In such a world, you cannot freely choose a setting corresponding to a combination that does not exist. There is no conspiracy involved, and nothing is being arranged. Some configurations simply are not there to be selected, and the appearance of a constraint on your choices is what it looks like from inside, when the space of possibilities is smaller than you assumed. There is one more piece of Tooft's picture worth having, because it answers an objection people raise immediately. If the underlying system is a simple deterministic machine, how can it possibly produce something as rich and strange as quantum mechanics without being tuned to an absurd degree? His answer is that information is lost as the machine runs. Different underlying states evolve into the same later state, so the past cannot be reconstructed from the present, and enormous numbers of distinct configurations collapse into a single equivalence class. What we call a quantum state is, on this view, one of those classes. The apparent probabilities are the sizes of the classes. Nothing has to be fine-tuned, because the machine is not aiming at anything. It is simply forgetting, at a rate that produces exactly the statistics we observe. The most prominent living advocate is the theoretical physicist Sabine Hossenfelder, who with the Oxford mathematical physicist Tim Palmer published a paper called Rethinking Superdeterminism in the journal Frontiers in Physics on the 6th of May, 2020. Her position starts from somewhere other than entanglement. She argues that quantum mechanics contains a genuine internal inconsistency, that the theory has 2 different rules, one for how systems evolve when nobody is measuring, and another for what happens when they are, and that no amount of interpretation removes the fact that the theory does not say which is which, or when to switch. That is the measurement problem, and she regards it as a real defect rather than a matter of taste. Her claim is that superdeterminism is the only approach that repairs it without giving up locality, and, this is the part that makes her unusual, that it is testable. The third figure is Tim Palmer himself, and his background is the strangest and most interesting of the 3. He trained in general relativity, then spent a career as one of the world's leading weather and climate modelers, working with chaotic systems and the geometry of what such systems settle onto. His proposal, which he calls invariant set theory, is that the universe's state moves on a fractal set in the space of possibilities, and that any state not lying on that set is not a physical state at all, not unlikely, not forbidden by some force, simply not a thing. If that is right, then the counterfactual question at the heart of Bell's theorem, what would have happened if the experimenter had chosen the other angle with these same particles, may have no answer, because that combination is not a point on the set. Palmer is careful to insist this is not a conspiracy, but a geometric constraint, of the same character as asking what a system would do at a state that violates conservation of energy. The question feels meaningful and is not. And there is a fourth family, close enough to mention, that most people find easier to swallow while it does the same work. Retrocausal approaches, associated with Hugh Price, Ken Wharton, and the 2-state formalism developed by Yakir Aharonov, propose that the future setting influences the past state of the particle, so the correlation is established backwards, along the light cone, rather than forwards from a common origin. It also violates the third premise. Its supporters argue it is more modest, because it only involves the small region between preparation and measurement, rather than the whole past. Its critics reply that an influence which travels backwards in time, but can never be used to send anything, is doing exactly the same job as a correlation from a shared past, with additional machinery bolted on. Bell died on the 1st of October 1990 of a cerebral hemorrhage at the age of 62. He had been nominated for the Nobel Prize that year and would very likely have received it. He had spent 26 years knowing that his theorem had an escape hatch, having described that hatch more precisely than anyone else alive, and having decided he could not live in the room it opened onto. He left it on the record anyway, which is a particular kind of intellectual honesty, and the question was still open when he died. It is still open now. There is something worth sitting with in that. We are used to the idea of a scientist who discovers an uncomfortable truth and defends it against a hostile world. This is the opposite shape. Bell found the most decisive argument in the field, and the argument came with a door attached, and he could see exactly where the door led, and he did not want to go there, and he told everyone about the door anyway, repeatedly, in print, in interviews, for the rest of his life. He could have left it out. It is a subtle enough condition that almost nobody would have noticed for decades. He wrote it down instead, and then spent 26 years hoping somebody would find a reason it was closed. Nobody has. So why does almost nobody accept it? The answer has very little to do with the physics. Before we get to what superdeterminism costs, I want to put the whole menu in front of you, with the prices marked, because the only fair way to judge one of these is against the others. Bell's theorem says at least one premise is false. Here is the complete list of ways out, and what each one takes from you. You can delete locality. This is the mainstream position, and its most fully worked out version is the pilot wave theory, sketched by Louis de Broglie in 1927, and rebuilt properly by David Bohm in 1952. In it, particles have definite positions at every moment, and always did, guided by a wave that fills space. It reproduces every prediction of quantum mechanics exactly. The price is that the guiding wave depends on the arrangement of the entire system instantaneously, everywhere, which requires a preferred definition of now, a universal present moment, and relativity says there is no such thing. Bell admired this theory enormously and said its non-locality should have been celebrated as a discovery about nature rather than treated as an embarrassment. You can delete definite outcomes. This is the Everett interpretation, published by Hugh Everett in 1957, usually called many worlds. The equation never stops applying, nothing collapses. The observer simply becomes entangled with the system, and all outcomes occur in branches that stop being able to affect one another. Locality is restored, determinism is restored, at the level of the underlying equation. The price is an unbounded number of unobservable worlds, plus a problem nobody has fully solved about why probabilities should come out the way they do when everything happens. Everett himself got a cold reception when he presented it in Copenhagen in 1959, left academic physics entirely, and spent his career in defense work. The idea was revived a decade later by Bryce DeWitt. You can delete the idea that the quantum state describes the world. This is where you find approaches that treat the state as a record of an observer's expectations rather than an inventory of what is out there. If nothing physical was ever correlated, then no mechanism is needed to correlate it. The price is that you have exchanged a problem in physics for a problem in philosophy, and you owe an explanation of why different observers' expectations always agree with each other. You can modify the equation. Objective collapse models, the best known, published by Girardi, Rimini, and Weber in 1986, with a gravitational variant proposed by Roger Penrose, add a genuine physical process that destroys superpositions at a rate depending on mass, so that particles can be in two places and cricket balls cannot. This is the only option on the list that makes new predictions and is being actively narrowed by experiment, which is very much to its credit. Its parameter space has been squeezed by orders of magnitude since the 80s. It has not been ruled out, and it has not been confirmed. And you can delete statistical independence. That is superdeterminism, and everything else stays. Locality, determinism, one world, definite properties, no collapse, no branching, no signaling. On any ordinary accounting of what is being given up, this is the cheapest option on the menu, which raises the question of why it is the one nobody takes. Here is the price, and it is not small. Stop for a moment and do something. Imagine there are two dials in front of you, and you may set either one to any angle you like before a photon arrives. Nobody is watching. Nobody is instructing you. Take your time over it. There is no hurry. Turn one of them slowly and feel yourself deciding, that particular sensation of the outcome not yet existing, of two futures both available, of the thing being genuinely up to you. Settle on an angle. Notice that you could have picked another one. Now hold that feeling and look at what it is made of. The hand that turned the dial is a physical object. The nerve that moved the hand carried a wave of sodium ions across a membrane, and the ions obeyed the same electromagnetic law that governs the photon now traveling toward your detector. The decision that fired the nerve was a pattern of activity in a network of cells that have been running continuously since before you were born, shaped by everything that has ever happened to you, made of atoms assembled in stars that died before the sun formed. And the photon in the apparatus was made in a crystal that was grown from elements with the same history. These are not two independent systems that happen to meet in a laboratory. They are two regions of one physical process that has been going on, without a break, for 13.8 billion years. The question superdeterminism asks is not whether you felt free. You did. The question is whether feeling free is the same thing as being statistically uncorrelated with a photon. That is the price. Not free will in some abstract theological sense, but something more concrete and more troubling for a scientist. The assumption that an experimenter can be independent of the thing being experimented on. That assumption is the foundation of the randomized controlled trial. It is the foundation of the entire method of varying one factor and watching what changes. If it fails as a matter of physical law, then in principle no experiment anywhere is fully clean. And although in practice the effect would be undetectable outside the specific setting Bell described, the principle is what people find intolerable. The objections are serious and deserve to be stated properly, not waved at. The strongest technical one is fine-tuning. In 2015, Christopher Wood and Robert Speckens argued that any attempt to explain quantum correlations by ordinary causal means without non-locality requires the parameters of the model to be adjusted with extraordinary precision, precisely enough that no signaling becomes possible and no trace of the underlying correlation ever shows up anywhere except in the Bell statistics. A model that has to be balanced that finely, they argued, has not explained anything. It has encoded the answer by hand. The reply from Hossenfelder and Palmer is that the fine-tuning objection assumes you can put a probability measure over possible universes and say that this one is improbable, and nobody knows how to define such a measure. And more importantly, that fine-tuning is only mysterious when nothing enforces it. If there is a dynamical law that drives systems onto a constrained set of states, Palmer's fractal set, T. Hooft's ontological basis, then the tuning is not a coincidence that has to be maintained. It is what the law does. We do not consider it a suspicious fine-tuning that planets are found on conic sections rather than on arbitrary curves. The other objection is the one Anton Zeilinger has made repeatedly and forcefully, that the assumption of free choice is a foundational assumption of science, and that giving it up means giving up science. This is honest, and I think it is felt sincerely by almost everyone in the field. But notice its shape. It is an argument from consequence. It says, the idea must be false because of what would follow if it were true. That form of argument has an unimpressive record in the history of physics. It was used against a moving Earth, against an old Earth, against natural selection, and against the heat death of the universe. Nature has never yet shown any interest in whether a fact is convenient for our methods. And then there is the thing that makes this more than a debating society, which is that Hossenfelder has proposed an actual experiment. Her reasoning goes like this. If there are hidden degrees of freedom underneath quantum mechanics, they must change over time, and they must have some characteristic timescale over which they scramble. Standard quantum mechanics predicts that repeated measurements on identically prepared systems give independent random results, forever, with no memory. But if the hidden variables have not had time to reset between one measurement and the next, the outcomes should not be independent. They should show a serial correlation, a faint pattern in the sequence, a hint that the third result knows something about the second. So, prepare the same state repeatedly, measure it, and increase the repetition rate until you are measuring faster than whatever the underlying timescale is. Look for structure in the sequence where standard theory says there can be none. She has argued that the most promising place to look is where the hidden degrees of freedom would be least disturbed, at low temperatures, at low energies, in systems with few particles. And she has pointed out something that ought to make this irresistible. The experiment is cheap. It does not need a new collider or a satellite. It could plausibly be done on existing quantum optics or single-spin apparatus by a competent group that wanted to. Nobody has done it. The reason nobody has done it is not that it has been tried and failed, and it is not that the equipment does not exist. It is that proposing to test superdeterminism is a difficult thing to put in a grant application, and physics, like every human activity, has subjects that are respectable and subjects that are not. So which one do you delete? Earlier that was a puzzle with 3 options and no obvious answer. Now it is a question about you. Are you willing to give up locality and accept that something reaches across the universe instantly? Are you willing to give up single outcomes and accept that everything that can happen does? Are you willing to say the wave function was never about the world? Would you rather change the equation? Or are you willing to say that the angle you were going to choose and the photon that was going to arrive were never quite independent of each other, which costs nothing at all in the mathematics and everything in the way you think about yourself? It is worth knowing that there is no consensus to defer to here. In 2011, at a Foundations conference in Austria, someone handed out a questionnaire asking the attending physicists which interpretation they favored. The Copenhagen family came first, with a little over 40%. Information-based views took about a quarter. Many worlds took under a fifth, and the rest scattered. The authors of the poll were the first to say the sample was small and self-selected, and should not be taken as a measurement of anything. But it remains the most cited data on what physicists actually think, and what it shows is a field with no settled answer and a comfortable majority position that is less a theory than a decision not to ask. There is no experiment that decides between them. Most physicists have no preference and do not need one to do their work. Of those who do, the great majority reject the last option, and their reasons are partly good arguments and partly something else. And the reality that last option describes is where we are going now. So here is the answer to the question we started with, stated plainly, the way I promised. The wildest theory in physics is not many worlds, and it is not a hidden dimension, and it is not a universe made of strings. It is the quiet proposal that when you choose which measurement to perform, that choice was never independent of the thing you were about to measure, and that this is why the particles appear to be coordinated across impossible distances. There is no signal. There is no reaching across space. There is no branching. There is a universe running forward under local laws, in which the photon and the physicist and the angle of the filter are all pieces of one continuous physical process that has never once had a gap in it. And the reality that description implies is the one we may not be able to handle. Not because it is frightening in the way a black hole is frightening. It is not violent or enormous or hostile. It is something quieter than that. In such a universe, nothing was ever undetermined. Not the results, not the experiments, not the decision to run them, not the 60 years of building machines to find out, not the conversation you might have about it tomorrow. Let me describe it slowly, because it is worth seeing clearly rather than flinching from. Imagine a film. The ordinary way to think about time is that the film is being made as it goes, that the next frame does not exist until the projector reaches it, and that what happens in it depends on things that have not been settled yet. The picture we are describing is different. The film is already on the reel, all of it, every frame, complete. Nothing is being decided as the light passes through. The frame you are in right now is one of them, and it contains you, lying there, hearing this, and the sensation of the next moment being open is itself one of the things printed on the film. That is not a new idea, it is very old, and one of the strange features of this whole subject is how directly the physics runs into things people have been saying for centuries. In 1814, Pierre-Simon Laplace described an intelligence that knew the position and momentum of every particle in the universe at a single instant. For such an intelligence, he wrote, nothing would be uncertain, and the future, as well as the past, would be present to its eyes. He meant it as a description of what Newton's laws implied, and he was not troubled by it. What superdeterminism adds to Laplace's picture is only that the intelligence would also have known which experiment you were going to run, and that this is why the photons come out the way they do. And of course, the older traditions got there first, in their own language. There is an Arabic word, maktub, meaning it is written. There is the Calvinist doctrine of predestination. There are the Stoics, who held that everything follows necessarily, and that wisdom consists of understanding this. I am not suggesting that physics has vindicated any of them. A deterministic universe requires no author, and the mathematics has nothing to say about meaning or purpose or fate. But it is worth noticing why this particular technical claim provokes a reaction out of all proportion to its content. It is because we have heard it before, and we have never much liked it, and now it has turned up wearing a laboratory coat. Which brings us to Einstein, and to the sentence everybody knows. God does not play dice. For a century that line has been the epitaph on his failure, the great man who could not accept that the universe has genuine randomness at its base, who spent his last 30 years on the wrong side of the argument, who was refuted by his own colleagues, and then by 50 years of experiment. In a superdeterministic universe, he was right. There is no randomness, there is no dice. The apparent chance in every quantum measurement is our own ignorance, exactly as he said, and the world underneath is as orderly and definite as he always insisted it must be. But the price of his being right is not the comfortable, sensible world he wanted. He wanted a universe where things have properties and where physicists are free to go and find out what they are. He would have got the first half. The second half is what has to go. In the world where God does not play dice, the physicist does not choose either, and the experiment that proved the point was itself something that could not have gone otherwise. He asked for a universe that made complete sense, and the version of that universe on offer is one in which he was always going to ask. I said earlier that I would come back to this, and I want to say it once more in different words, because it is the whole point, and because some of you will have drifted a little by now, and that is entirely as it should be. The thing that would explain entanglement without any spooky action, without anything moving faster than light, without any splitting of worlds, is the possibility that the experimenter's choice and the particle's hidden state were correlated all along, because they came from the same place. That is superdeterminism. It is the cheapest option in the mathematics, and the most expensive one in every other sense, and it is the only one Bell himself bothered to describe in detail before turning away from it. We should be careful, at the very end, to separate what is settled from what is not. What is settled? Entangled particles produce correlations that no local instruction set can reproduce. That is established beyond any reasonable doubt, to confidence levels no other claim about reality has ever reached. What is settled? Nothing can be used to send a message faster than light, and nothing ever will be. What is settled? At least one of the three premises behind Bell's theorem is false. What is not settled? Which one? That is open. It has been open since 1964. It was open when Bell died in 1990, and it is open tonight. The loophole he identified cannot be closed by any telescope, because it lives in the 4% of our own past that no instrument can reach. The one experiment that might settle it has been proposed, and costs very little, and nobody has run it. So we end where we began. You are holding a die. Alice is holding the other one, 7,000 miles away, in a room you will never see. You throw yours, and it turns over on the felt, and it settles, and it shows a 2. And in that instant her die shows a 5, and the two numbers make 7, exactly as they always have and always will. Only now the picture has changed. There was no moment when your die was undecided in the air. There was no instant in which something crossed the Pacific to tell hers what to do. There was no branching, no collapse, nothing reaching, nothing choosing. There was a universe going about its business under local laws, in which the number on your die and the number on hers and the moment you decided to throw were not three separate facts that had to be reconciled with each other. Nobody had to be told anything, because nothing anywhere was ever waiting to find out. We do not know whether that is the world we live in. It might not be. Most of the people who have thought hardest about it believe it is not, and they may well be right. But it has not been ruled out, and it cannot be ruled out by the methods we have, and the reason it makes us so uncomfortable has less to do with the evidence than with the fact that the theory includes us, and we are not used to being inside the equations we are solving. Thank you for spending these hours with me, out at the edge of what physics can actually say about reality. If this kind of slow, careful walk around a difficult question is your sort of thing, a like or subscribe would mean a great deal. It helps me keep making them. And the next time you feel yourself deciding something, remember that physics has never once been able to prove that you were. Good night, and may you never look at a pair of dice the same way again.